We're back with another tutorial, and this time we're diving into k-means clustering with JAX. While we'll touch on the theory underpinning this clustering technique, our main goal will be to demonstrate its practical application, leveraging the JAX framework. We'll also weigh its strengths and weaknesses against a NumPy-based approach. To ensure this tutorial is accessible and easy to follow, we're going to utilize Jupyter Notebooks on the Google Cloud Platform. But don't worry, you're more than welcome to work within the Python environment you're most comfortable with. For simplicity, we'll use TensorFlow Enterprise for the environment starting point, then tweak things as necessary. This gets us started with a lot of necessary packages, but don't forget that we'll be using JAX once our environment is up and running. To give the environment some extra horsepower, we'll throw in a GPU. A simple and relatively inexpensive T4 should suffice. Once we're comfortable with the remaining settings, it's time to create our environment. As it's firing up, let's have a quick chat about k-means clustering. It's a nifty and relatively simple algorithm for grouping multidimensional data points, also known as vectors. Imagine that you're looking to cluster a set of data points in a two-dimensional space. Thinking visually, you might identify 3 clusters in the top left, bottom, and top right. The tricky part is making a machine do this sort of clustering without our subjective visual interpretation. This is where k-means clustering saves the day. We initiate random points for the center of potential clusters, also called cluster centroids. Here we'll opt for 3 of these randomly placed centroids and then determine the closeness of data points to these centroids. We'll then assume that each point belongs to its closest centroid, meaning we have cluster assignments for each of our data points. The magic then comes in that we calculate a new centroid based on the mean of these clusters. Repeat the process until no more centroid changes are produced, a status known as convergence. Once our notebook is live, let's proceed with writing our code. We have a couple of pre-run package installations. Specifically, we ensure that JAX is set up with CUDA enabled to leverage our GPU. We'll also confirm that the GPU is in use for our JAX calculations. After importing the necessary libraries, we'll start with a function to place our initial cluster centroids randomly, and we'll follow that with a function to calculate distances between these centroids and our data points. The most commonly leveraged distance metric is Euclidean distance. The computation might seem complex when we're in a high-dimension space, but you can think about it as the Pythagorean theorem generalized to multidimensional space. It's a sort of multidimensional straight-line distance between points. Therefore, unsurprisingly, the calculation looks quite a lot like the Pythagorean theorem with the square root and sums of squares. We'll then assign our data points to the nearest centroids and calculate the mean of those data points to use as our new cluster centroid positions. Having these functions ready for our steps, we integrate them to create our k-means function, which accepts embeddings, input data, a number of clusters, and a maximum iterations value. This function sets the algorithm in motion. To illustrate, we will input some simple two-dimensional data, but remember that in real machine learning applications, the dimensions are often in the thousands or higher. Thinking about this visually, we'll have a couple points in the top right of the XY space and a couple others in the bottom left of the XY space. We also need to ensure that the data type for these vectors is compatible with the JAX computations. We'll achieve this conversion using the JMP array construct. We'll also review the duration of these calculations with the timer and execute the k-means function to cluster the data points. Lastly, let's run this calculation without timing it so that we get a print of the results. As you might intuitively suspect, the algorithm has clustered the first 2 points into a cluster 1 and the remaining points into a cluster 0. Let's now quickly compare to an alternative non-JAX method by transitioning this JAX code to NumPy. For this, we need to adjust a few elements in the code. First, let's duplicate our centroids code and make minor changes. Notably, we'll need to handle our random number seeding differently. The distance computation is also quite simple. It's essentially the same version as we implemented with JAX. Now, the assignment of clusters begins to differ somewhat as NumPy doesn't have a direct equivalent for JAX's VMAP. In this case, we'll use the apply along axis function from NumPy. The update centroids function is extremely similar. Again, the only difference lies in switching out JAX for NumPy. The structure and logic of our k-means function within NumPy remain mostly similar. Now, let's compare how the NumPy and JAX models perform. We'll rerun them and see that NumPy on the CPU executes significantly faster than the JAX model, which uses the GPU. This isn't exactly fair though, as the compilation and vectorization features from JAX have a much larger impact for non-trivial vector sizes and vector counts. Let's optimize the JAX-based code and increase the scale of the problem a bit to turn the tables. For example, we can better establish constants upfront and better use JAX function compilation to improve performance drastically. When we use the JAX random package for generating random vectors, note that it's different from standard Python or NumPy. We're highlighting a common mistake here. Using the A key for random number generation does not modify it, so we'd keep getting the same random number. However, this can be rectified by using a split function, which will generate a new random value each time as desired. So let's run our new JAX code with the adjusted vector size and larger count of vectors. Doing so, we find that the execution time drops significantly. In a comparative run using the NumPy methodology, we find a much larger runtime than the smaller NumPy test and observe that the total execution time exceeds that of JAX a few times over. The key takeaway here is that as vector counts and vector lengths scale up, and once we optimize our JAX code for more efficient compilation, vectorization, parallelization, and execution, we'll typically see meaningful performance improvements over traditional approaches like NumPy. We hope this video tutorial was helpful. We'll keep an eye on the comments section for any questions and remind you to please enjoy responsibly.